taking a look at this problem right here. So those of you looking at this on YouTube later, you want to pause it here. And we were finding the average value of this function on the interval from 0 to the square root of 8. So here's my work running through that. To do that, I double checked a couple of things in Geogebra over here. And so if x equals 0, y is negative 19. If x equals the square root of 38, y is positive 19. So we're trying to find the average y value along this part of the curve, and it turns out to be at negative 6 1/3 right here. All right, brief summary of the problem that I did not share with the screen. Sorry, Gerald and everyone else. All right, so next problem. So here we have y equals x squared, and we are concerned about the interval from 0 to 1, and we want to calculate an upper sum with n equals 4. So to do that, we need to consider the function and the interval. I'm going to graph them both together here. So here is 0, here is 1. 1 squared is also 1. 1/2 squared is 1/4. So here's a few different points. So the graph starts shallow and then gets steeper. We want to do 4, so then we'll have to break this into 4 parts down here. So we'll have 1/4, 1/2, or 2/4, and 3/4 as our significant x values. And so we'll break it into rectangles. Wrong button. Our upper sums here are going to be left endpoints or right endpoints, combination. What is it? Yeah, because it's increasing their right endpoints, and so our rectangles should look like this. So for each of these, the delta x, is equal to the width of the interval divided by the number of rectangles I want. So that's 1/4. We usually go for a fixed width, but we don't have to. And then the particular x value, since we're using right endpoints, you take the left endpoint 0, and then you add on multiples of delta x. So I times 1/4. So we get 1/4, 2/4, 3/4, and then finally 4/4 for the last evaluation. So if I were going to write this as a sum, which I actually didn't ask you to, the sum would look like this. The sum as I goes from 1 to n of the base of the rectangle 1/4 times the height of the rectangle, which would be the function evaluated at those points. So times I over 4 to the second. So that's more than what I asked for here. Here I just said, find the area of each rectangle, add them up, right? Find the upper sum. But I am going to ask you later in the test to demonstrate a sum formula for a particular function. So we're warming up to that. So in this case, I would have 1/4 times each of those evaluations, which would be 1/4 squared plus 2/4 squared plus 3/4 squared plus 4/4 squared. And so we whip out our calculator and come up with a number there. So let's make sure we're all getting the same number. GeoGebra does have a sum command. I'm not sure if Desmos does. I haven't used Desmos in a while. Let's check out Desmos for fun. Desmos graphing calculator. Can Desmos do a sum? Ooh, it can. Sweet. So we want the sum from 1 to 4. And they're using n as the variable of summation, not I. And then I have a 1/4 times parentheses. I would call it n over 4 for Desmos. raised to the second power. And so that should be the sum I want. Desmo says it's about 4.6875. Anybody else get that on this one? Okay. Double checking in Google calculator. Each one has a 1/4 in it, so I factored that out. And then I have a 1/4 squared, which requires lots of parentheses. Actually, that one really doesn't. Plus 2/4, which is a half. Now this one lends itself to entering decimals, but some of them do not. If I had thirds in the denominator, oops, plus what's next, 3/4. And then finally 4/4, which is just 1 squared or 1. And so regular calculator agrees it's about 0.46875. Actually, it's exactly 0.46875, which is probably some amount of sixteenths. Anyone get a fractional answer on that one? How many sixteenths is that? Oh, it reduces to 15, 30 seconds? Okay. Oh, yeah, right, okay. Because we're going to have 60/4, and then it reduces down to 30 seconds, right? Yep. Cool. All right. Let's see, that wasn't too bad. Let's try another one. So again, draw sketch, we got that. You might need to know some sum formulas like I squared, or I cubed. Oh, question? Yep. Yeah, that's a good question. So if it's decreasing, would you use left endpoint? So if, for example, our function looked like this here, and we were partitioning it like that, and we draw those vertical lines up, to get an upper sum, we would have to switch to left-hand endpoints, right? Yeah, so you got to be careful. There's the problem, say upper or lower, left or right, and if it increases and then decreases in the same interval, you have to jump back and forth between left-hand and right-hand endpoints, right? That's why I usually avoid talking about upper and lower sums. They're a pain in the butt if the function changes from increasing to decreasing. Yeah, good question. All right. So let's see what else looks cute on here. Let's see, some summation formulas. Oh, did anyone get this one here? What function would this be the integral of? So picking that apart, oops. Screenshot of that. So limit of the Riemann sum is the definition. Let's move that out of there in a new page. Is the definition of the definite integral. And so looking at this, I would say this right here, especially based on that, is my delta x. Okay. So this right here must have something to do with my function. Okay. Now I'm starting at 0. Right? So that means my x sub i's are going to be, if I were doing right-hand endpoints, would be, so for right endpoints, would be 0 plus multiples of delta x. Well, if I'm using k as the variable, wouldn't they be then 4k over n? If delta x is 4 over n? Okay, so k is my multiple of 4 over n. So those are my xi's. So each xi looks like that. So that means this right here is really the function in terms of x, 1 over x plus 1. Oh, lost my pen. That makes sense where I'm getting that? Because these guys are my xi's right there, and these are my delta x's. So that must be the function that I'm trying to evaluate right there. Now notice I didn't ask you to take this limit. And it turns out we don't have any means to do so at this time. So given an n, you can tell me what the sum is by plugging in something like GeoGebra or Desmos or a spreadsheet, but we don't have a means at the moment of finding that limit. We haven't learned any algebra that will help us do that. Well, so if I wanted to find this limit, and I don't know algebra how to do it, what's my other means of finding a definite integral for this guy? If I can't take the limit of a sum. So my claim, right, is that right there is really the integral from 0 to 4 of 1 over x plus 1 dx. We don't have any means to come up with the limit. Are there other ways we can come up with this answer? What tools do we have in our belt now? Yeah, we can come up with an answer. The fundamental theorem of calculus says, hey, if you have an antiderivative for that, you can solve it. Okay. Do we know an antiderivative for 1 over x plus something? What is it? Kezia, you know this? No? What if it were just a 1 over x? What's the antiderivative for 1 over x? Natural log. Does a plus 1 really affect anything? If you're not sure, do we use substitution? So let's try it. So right now I'm doing all this question asked for was that. But then I thought, I want to know the answer. What's the limit? Okay. We don't have an algebraic means to find it, but we do have the fundamental theorem of calculus. So let's just take it a step farther just for fun. So the new question here is if I go from 0 to 4, 1 over x plus 1 dx, can we do a u substitution on that, thinking that this is related to the natural log? What would u be here? X plus 1, beautiful. Yep. U equals x plus 1. So then du is just dx, right? That's nice. So ignoring the boundaries for a minute, this would be the integral of 1 over u du. And I know an antiderivative for that is the natural log of the absolute value of u, and maybe a plus c. So now I can reverse substitute and say that this red guy here has to be equal to the natural log of the absolute value of x plus 1 evaluated from 0 to 4. And don't forget that absolute value. It is important depending on what the boundaries are. Now here, since our boundaries are all positive, no big whoop, but sometimes it is an issue. All right, so let's see, what are we going to get then? If we plug in the 4, we're going to get the natural log of 5 minus the natural log of 1. And I love the natural log of 1. What's it equal to? 0. Yeah, that's wonderful. So this thing happens to be just whatever the natural log of 5 is. And we could check that with a piece of technology to make sure. All right. So we were able to evaluate that limit, but only using the fundamental theorem of calculus, right? We couldn't evaluate the limit directly, which is all right. We found a way. All right. Were there any other problems on the practice test people wanted to take a look at? Let's see. Oh, here's one where I actually wanted you to take the limit. The area one here is from an example I did in class when I introduced the fundamental theorem of calculus. And then we have some applications of the first part of the fundamental theorem of calculus. Indefinite integrals, some of which involve substitution. Is total area different from a regular integral? Yeah, because with a regular integral, if I integrated from -4 to 4 on this, I would get 0 because the negative heights and the positive heights would balance. But total area says ignore the negative heights and just give me the area of both parts, right? So they are different questions. You want to pay attention to. If it says total area, flag should go up and say, ooh, I got to be careful if there's any negative parts of the function. All right, so any requests on problems 6 through 11 or 6 through 20? guys are so quiet today. Go up. No takers, I get to pick? Okay. Okay, I'm glad you asked. Thank you. 18 is probably an area between curves. Yep. All right, find that area enclosed by the graph square root of x and negative x plus 2 and y equals 0. And we want to draw it. Okay, square root of x, negative x plus 2, y equals 0. Let's do it. All right, my colors are missing as usual. Let's go black. So we've got y equals the square root of x, y equals negative x plus 2, and y equals 0. And graphing utility would be the quickest thing to do on a test, right? And then maybe make a sketch on paper. I'm just going to go for this. Let's see, the square root, 1, 2, 3, 4. Hopefully that's far enough over. 1, 2. Square root of 0 is 0. Square root of 1 is 1, and the square root of 4 is 2. So that's a rough sketch of the square root function. Negative x plus 2, y-intercept is 2, and then the slope is negative 1, so down 1 over 1, down 1 over 1. Here is that function right there. And then we're also throwing in y equals 0, aka the x-axis. So the region bounded by the 3 of these looks like this region right here. So to do that, I'm thinking, switch color, there we go, that either I'm going to split the integral into 2 parts at x equals 1, because the top switches functions from black to blue at that point, or I could try integrating with respect to y, integrate horizontally. Somebody pick for me, please. Y? Okay, we're going to integrate with respect to y. So then I have to restate these as functions of y. So the black function would be x equals y squared. Oops, y squared. And the other function, let's see, if I bring the x over and the y back, is pretty symmetric. It would be x equals negative y plus 2 would be the blue function here. And I probably should have colored that blue. Let's see. There we go. All right, and so the blue function is on top when we look at this with horizontal rectangles, okay? Because x moves in a positive direction that way. So then this blue function is my upper with respect to y, and this guy is my lower. And what are the bounds of integration here? From 0 to 1, yeah, right through there. So I think we want the integral from 0 to 1, and I'm just going to remind myself this is a y values I'm plugging in, not x values. And then my upper function is y, negative y plus 2 minus my lower function y squared with respect to y. So I can do this integral in one shot instead of 2 parts. If it turned out it was hard to solve for x, I would give up on that idea, but this isn't too bad. So antiderivative here would be what? Negative y squared over 2 plus 2y minus y cubed over 3 from 0 to 1. And that evaluates to what? Negative 1/2 plus 2 minus 1/3. And what happens when we plug in the lower boundary here? I get a whole bunch of zeros, okay? On a test, it's worth writing that down to make sure you really believe that instead of just thinking it, because a test is different pressure than homework in class. But I feel good about that. All right, so let's see. 1/2 and 1/3 is 5/6. So I want 2 minus 5/6. which is 1 1/6. So I think this is 2 minus 5/6, which is 1 1/6. So somehow, anybody with a calculator, is that 1.166666666? So it looks like we got it. And I don't know if anybody noticed, I posted my solutions to this morning, so you can see what I wrote down for each one aside from this. All right, we got time for 1 or 2 more. That was fun. All right, so let's see. I think you saw this one multiple times in the homework. Let's look at that just for fun, unless somebody has something they want to do more. Okay, so let's try it. New page. So we want to find an indefinite integral for the cotangent, and did I use x or theta there? Theta, okay, theta d theta. Oh, you guys want to see a trick question that my calculus teacher put on a test once? There's my pen. And I can't remember if I fell for it or not. Come on, give me a different pen. The question was, what is the integral of, I can't remember the exact function, but it could have been something like the cotangent of theta. But he wrote with respect to x. What's the variable of integration here? X. So cotangent of theta has no x in it, right? Which means it's technically a constant. So the answer here is cotangent of theta, which is a constant with respect to x, times x. Okay. I will try not, and he wasn't clear after whether he just, that was a typo on the test or he really was trying to mess with us. But the variable integration matters, right? It does definitely matter because that's, the red thing is not the problem we have here. All right, so let's get rid of that. All right, so kind of the moral of that story is be careful of the variable of integration. And if anything seems weird on the test, don't be afraid to ask. Worst I can say is I can't answer your question. Yeah. All right, so rewriting this right here. If I don't recognize this function as a derivative of something off the top of my head, then I rewrite in terms of sines and cosines. That's a good practice with trig stuff. So this would be equal to the integral. Let's see, tangent is sine over cosine, so cotangent is cosine over sine. And then generally, if you have a fraction involved with other stuff, the safe bet for a u substitution is to pick the denominator, which is a good guess here because, you know, the derivative of the sine is the cosine. So if we let u equal the sine of theta, then du has to be the cosine of theta times d theta. And so u substitution is quite slick here. Cosine times d theta, that's just du, which leaves me 1 over sine, which is really 1 over u. And antiderivative of 1 over u, natural log of the absolute value of u. Try not to forget about that absolute value. And then reverse substituting, I get an antiderivative of the natural log of the absolute value of the sine of theta plus c. Now, if this were the test, are you done? I would check, right? If you have time on the test, check everything you can, right? So what I would do here is just, you know, double check. Is it true that the derivative with respect to theta of the natural log of the absolute value of the sine of theta, oops, forget about the plus c, is it really equal to our cotangent? Now, we got a bit of a problem here because the derivative of a natural log is a bit messy. And so I'm just going to make believe it doesn't exist for now. A common formula for the derivative of the absolute value is usually the absolute value of x over x. And think about that for just a second. Here's the absolute value of x, right? It's that V-shaped curve. It equals y equals x on this side and y equals negative x on that side. What's the slope on the right side? 1, and the slope on the left? -1. And so if you think about it, if you plug in any x value out here like 2, absolute value of 2 over 2 is 1. But if you plug a number in over here like -2, you get positive 2 over -2, which is -1. Okay. And there's really no good way to derive that. It's just an observation that this is a way to deal with it. And if we throw that into the chain rule with the problem we have right now, it's going to be quite messy and not quite evaluate right. So my point for now is we're just going to ignore the absolute value for now. Otherwise, it gets very messy because we have to evaluate positive versus negative. All right, so antiderivative of the natural log. Oh, sorry, derivative of the natural log. 1 over whatever's inside. So that would be 1 over sine of theta. But the chain rule applies here, right? Chain rule says you have to take the derivative of the inside. Derivative of the sine is cosine. And we could view that as cosine over 1. So we get cosine over sine, which is definitely the cotangent. And I feel good now. Okay. So evaluation-wise, we absolutely need that absolute value. But when I actually try to compose it with functions and derivatives and integrals, it does get quite messy because it's a piecewise function. It's still doable, you just have to do it in parts. Yeah, because the absolute value, you have to, the bottom line, the definition, the true definition of the absolute value of whatever is equal to whatever if whatever is greater or equal to 0. So you have to break it into cases. It's equal to the opposite of whatever was inside if whatever was inside, that's an if, happened to be less than 0. So you have to break it into positive and negative cases. If it's a function that's periodic, which forever changes sign, you have to generalize those cases, and it's just, it takes a while to do. Yeah. It's not that we can't do it, it just, we don't have enough time today. All right, we got time for one more. Let's do a fundamental theorem problem. Let's do something like 8 and then 10. So an integral can be a function. So for example, I could integrate from 0 to x, t squared plus t plus 1 with respect to t. So that is its own function. I have to use integration to get it. The fundamental theorem of calculus says that you can differentiate that with respect to x and something magical happens. The integral operator and the differential operator cancel each other out and get evaluated at that endpoint at the top, provided this endpoint down below is constant. So this must be equal to x squared plus x plus 1. Just boom. That's what the fundamental theorem says. If you wanted to, you could find an antiderivative for this, evaluate the endpoints, and then differentiate it, and you will get back to that in the end. Right? So that's just more work to do the same thing. So if you're unsure on the test, like, oh, you're stressed out and you're struggling, find an antiderivative for this. Write it down, then differentiate it. See what happens. Okay, so let's just double check that quick. Antiderivative for this would be what? T cubed over 3, right? Plus t squared over 2 plus t. Now I don't have to do a plus c because I'm evaluating boundaries. So I plug in my x, and I get x cubed over 3 plus x squared over 2 plus x. And then when I plug in 0, I get a 0 cubed and a 0 squared and a 0, which is a bunch of zeros. So this is the definite integral for this particular function. Then I differentiate that with respect to x, right there. And what is the derivative of x cubed? 3x squared, the 3's cancel, leaving an x squared. Derivative of x squared is 2x, the 2's cancel, leaving an x, and the derivative of x is just 1, which is what the fundamental theorem claimed ought to happen. Okay, so the fundamental theorem is kind of a shortcut for a bunch of different things. Antiderivatives and derivatives, or that a derivative and integral cancel each other out. All right, next one, I think, was the integral from 0 to 2x of the sine of x. Is that the one I had down there on paper? Oh, and that's got to be a t, excuse me. And then we were also asked to take the derivative with respect to x of that. And the catch here is that this is not just a mere x. And so if we take the derivative of a function, and we have a function within that, the chain rule applies. So straight shot on the fundamental theorem says, well, you should get the sine of whatever that upper boundary is, 2x. But the chain rule for derivatives says you better multiply by the derivative of the inner function, which is up there. Derivative of 2x is 2. So the answer here involves the chain rule. Okay. The chain rule was secretly acting back here. What's the derivative of x? What happens when you multiply by 1? Nothing, right? So the chain rule is always active. It's always looking out for stuff. Sometimes we just don't notice it. All right, and that's about time for today. So I just sent out an email that said if you didn't finish by 5 or 5/6, but you get through at least half of them, we'll call that good enough. The more problems you do, the better you be prepared, the more comfortable you'll be with the things I throw at you. There is a review set of questions online also. And I sent out an email last night that said, I recommend doing them, but if you would rather do the paper test instead, give me your answers. I will grade it and then substitute that grade in for this if you don't have time to do both. Okay, so that's the deal. Otherwise, the test is tomorrow. It will be shorter than this, somewhere between half the length and 3/4 of the length of that one I posted. I will give you a sheet of derivative formulas to look at, and you can use a graphing type calculator, which includes Desmos on the test. All right. All right, have a good day, do good math and other stuff, and please get some sleep tonight. Who sleeps? I try to.